All right, in section 2 of chapter 7, we're going to talk a little bit about inverses of relations and also of functions. Now, I know this might seem like it's a little bit kind of different than what we had originally talked about, but basically what we're working towards is the fact that exponential functions and logarithmic functions are inverses of one another, and we kind of have to know how inverses work if we're going to talk about how to be able to kind of transform between one and the other. Okay, so what we're going to do is we're going to graph some inverses, and we're going to take a look at the difference between relation and function and how those are applied to each other when we talk about them being inverses of one another. And we're also going to find inverses. Now, it's one of those things where, honestly, this isn't entirely that difficult or anything like that. It's just a little bit different probably than what you've done before. Now, you probably should have done some inverse stuff in Algebra 1. All right, but again, even if you haven't, it's something that you should be able to pick up fairly easily as we move forward here. Okay, now you've seen the word inverse before in a lot of different things. Okay, when we were back to talking about basic properties of mathematics, we probably talked about additive inverses and multiplicative inverses. Well, basically, an additive inverse is just the opposite. Okay, you're performing the opposite action. So if you're adding 3, the inverse would be to subtract 3. Okay, likewise, when you're talking about multiplicative inverse, if you multiply by 5, the inverse of that would be to multiply by 1/5. Okay, essentially, one kind of undoes the other. Or if you do one to the other in terms of multiplication, you get 1. If you do one to the other in terms of addition, you're going to get 0. Okay, or they basically cancel each other out. Now, this can also be extended to inverses of matrices. We haven't talked a lot about matrices this year. It is something that you probably discussed in Algebra 1. So if you remember how that works, you would know how these down here are essentially related to each other in the same way or the same manner that additive and multiplicative inverses are related to one another. Okay? Now, the big thing here is the difference between a relation and a function. Okay, a relation is just a smattering or a scattered array of just different points that you can put on a graph. Okay, just a bunch of XY points you can put on there that aren't necessarily associated with each other in a real strict way. Okay, basically, if you want to take the inverse of a relation, you just reflect across the line y equals x, okay, which is kind of a diagonal line that has a slope of 1 and a y-intercept of 0, which we'll show you here in a minute. But essentially what you do is you just switch the x and y values around. All right, so if I have a point 2, 3, all right, if I want to find the inverse of that, it would look like 3, 2. Okay, you just flip-flop the x and y values around to find the inverse of a relation or the inverse of points. You could do the same thing with a function if you really wanted to. If you found all the points that are associated with a function, you could flip-flop the x and y's and all of those and graph the new function, and it would be the inverse of what you have going on. Okay? Basically, like we talked about at the bottom here, a relation is a set of ordered pairs that maybe or maybe do not have some type of association with one another. A function is a relation in which the x value has at most one y value. So when we're talking about a function is a relation, all right? But all the ordered pairs are related to each other in a specific way, or there's a set rule as to why they are where they are in relation to everything else that happens to be on your graph. Okay, so we're just going to start simple, graph the relation, connect the points, then graph the inverse, identify the domain and range of each. Okay, so if I were to go ahead and put these up here, 0, 2, 1, 5, 5, 6, and 8, 9. Something up here. Now, if we connect the points to those, you can see how they're not necessarily with each other in any other way. Okay, now if I wanted to graph the inverse, I would simply just flip-flop the points. So instead of 0, 2, I would go 2, 0 for my first one. Okay, I would go 5, 1 for my second one. And I would go 6, 5 for my next one. And I would go 9, 8 for my last one. Okay, now if I were to draw those in, Okay, I would get something that looks something similar but just reflected. Now, here's the idea with an inverse. The line y equals x would be a line that has a slope of 1 that goes right through the origin. Okay, now you can see how inverses are reflected over that line. So if you look at the top graph compared to the bottom one, if you were to fold it over that dotted line, those graphs would lie right on top of one another. Okay, we can take a look at things here. On the next slide, where it's probably a little bit better view, you can see the difference between the original, which is our blue, and the inverse, which would be our red line. Okay, inverses, they have opposite opposite x and y values. Okay, now I'll go back here a second. Identify the domain and range of each. Okay, now domain and range, when we talked about with exponential functions, was a little bit different because we wanted to include anything that could possibly be on that particular function. In this case, because you only have specific values, okay, if I'm looking at my domain here, my x values, basically the x values that would be part of my domain are 0, 1, 5, and 8. We'd say specific x value, then I probably should go something like that. X such that x is 0, 1, 5, and 8. In my range, oops, should be a y value there. I'll just list all my y values, 2, 5, 6, and 9. Okay, or if you just wanted to put range out in front, like write domain out here or a D out here, and then just put those numbers in parentheses, or put an R and just put those numbers in parentheses, it would mean the same thing. Okay, we have a specific x values and y values. Now, if we look at the domain and range of the inverses, they would just be flip-flopped. Okay, the range of the original would become the domain of the inverse. Okay, the domain of the original would become the range of the inverse. So that's kind of what we're talking about as far as these things are concerned here. Okay, here's just another example. We would plot the points. Okay, as far as the inverse is concerned, the inverses would just be flip-flopped. Okay, so if I have the point 1, 0, 1, 0, 3, 1, 4, 2, and 5, 3, and 6, 5, I'd have something that looks like this. Okay, now if I were to graph the inverses of that, I would be taking, and basically these would become the x values and these would become the y values. Okay, so I'd be looking at 0, 1, 1, 3, 2, 4, 3, 5, and 5, 6. Okay, something up there like that. Okay, and it looks like I might have made 6, 5. Oh, this point on the original should have been up here a little bit higher, so it should have looked like that. My fault. Okay, but again, if you look at everything that's going on, these would be reflected across that line, y equals x. And if you look on the next graph, this is just a little bit better picture of what those would look like. Okay, red being the original, or excuse me, blue being the original, red being the inverse of that. Okay, with just flip-flopped x and y values. Now again, if you go back, if you want to think about domain and range, okay, the domain of the original would be all of these values. The range of the original would be all these values. They would just be flip-flopped when you're talking about the inverse. Okay, so down here, these values on the bottom would be the domain of your inverse. These values on the top would be the range of your inverse. And because it's not a function, it's just a relation, okay, we can just list the individual x values and y values as our domain and range. Okay, if it were a function, we might have to go ahead and be a little bit more specific and kind of generalize anything that could possibly happen to fall on that particular function. Okay, and we'll get a little bit more into that later as we move forward with this. Okay, now as far as inverses are concerned, notation. Your original is going to look like this. If you're representing an inverse, you're going to write something that's like f to the -1 and then an x. That just represents notation for what an inverse is supposed to look like. Okay. Again, what we're going to start with here is just kind of thinking about how the opposites of all this stuff work? Okay, so taking an original, being able to figure out the inverse based on what's going on. Now if you look at what's going on here, if we take a 3 and we input it into our original function and we get a 9 out, on the bottom here we're trying to think about how can we take that output value, make it our new input value, and get back to what we originally started with. Okay, well, if you compare this box to the box above it, you can see how the only difference is instead of adding 6, we subtracted 6. So in our original compared to our inverse, we're just kind of undoing what was done to our variable in the original. In the original, we were taking x and we were adding 6 to it. So to undo that process, I take x and I subtract 6 from it. Okay? It's really kind of as simple as that. All right? You're kind of trying to figure out in terms of inverses, what did I do to the variable in one case? What can I do to undo it in the next case? Okay? So use inverse operations to write the inverse of f of x equals x minus 1/2. So in this case here, I'm taking and I'm subtracting 1/2 from the variable. So my inverse, or basically undoing that process, would be taking the x value and adding 1/2 to it. Okay? Inverse operations. What's the opposite of subtracting 1/2? Would be adding 1/2. So that would be my inverse. And just notice how I used the correct inverse notation right here on the graph. Or not on the graph, on this particular slide. Okay? Again, same idea. Okay, what am I doing to the x in the original? Well, I'm dividing it by 3. So that means to kind of undo that whole process to the variable, I would have to take that variable and I would have to multiply it by 3. So this becomes my new inverse. Okay? Again, not super duper complicated. Okay? You just have to make sure you understand kind of what the opposites of everything are that we have going on here. Okay? We've already kind of talked about this a little bit. We just have to make sure we remember, like it says on the bottom here for this hint, understand what the reverse orders of each of these operations happens to be. And we're not going to get super complicated with some of this stuff, but just remember, we talked about addition and multiplication in the previous 2 examples. Just kind of understand if something's being given an exponent, what you would have to do to counteract or kind of undo an exponent, and that would involve radicals. And just kind of beware of parentheses and how all that stuff's going to work. Now, speaking of parentheses, it's just one of these things here where basically, if you think about undoing what's being done to the x, okay, in this case here, we're subtracting 7 from the x, and then we're going to take the x times 3. So to undo that, I am going to take the x, I'm actually going to add 7 to it, and then I'm going to take it times 1/3. Now, this can be a little bit kind of confusing for us to think about. So let's think about what's going on right here. If I were just to take and distribute, okay, we'll look at that instead. Okay, 3x minus 21, okay, as my original, as opposed to what's originally drawn up there. Okay, well, if this was my original, I would be taking the x, okay, I would add 21 to it, and then I would be taking both of them and dividing by 3, which essentially would get you to the same thing that's listed down here. So I guess if you're going to go from this straight to this, what you should probably think about doing is just one of those things where look at what's being done to the x first. We always want to start from the x and work out. So the first thing shown here is we're subtracting 7 from the x, so that's why I started with adding 7 to the x. And then whatever would be left over after we would do that, we would multiply by 3. Well, kind of the same idea here, okay? That's why I just have the 1/3 times the x. So work inside out as far as all that stuff is going to be concerned. Okay, or if it helps you to distribute first, like I did when I got to here, and then kind of go backwards and say, okay, I would have to divide everything by 3, all right, and then I would have to add 21. Okay, essentially, that would get you to the same thing that we have going on here. Okay, but again, I can understand how those get to be kind of a tiny bit confusing sometimes. Okay, in this case here, again, we're going to start with the x. So what undoes that? We would multiply the x by 1/5, and then we would have to add 7. Okay, again, start with your x, undo whatever it says that your x has to be undone first, and then kind of work out to whatever would happen to be left over. Alright, so using inverse operations like we did there is one way to go about solving these things if you feel comfortable in understanding what the kind of the opposite operation of everything is. Now another way to do it from the beginning is we can flip-flop kind of x and y and go ahead and solve the other way around. So first things, I'm going to graph what's given here because that's what it says I'm supposed to do. So remember, graphing, it's in y equals mx plus b form, or essentially slope-intercept form for a function. So I'm going to plot the y-intercept, which would be -5. Alright, then I'm going to use my slope, which is -1/2. So I'm going to go, I can go down 1 and to the right 2, or I can go up 1 and left 2, which I'm going to do that up 1, left 2 a little bit because I got more room. Go like that. Okay, so this would be my original, and I'll just dot my original. Okay, so again, you're going to have to remember back to when we worked with lines, how to use the slope and how to use the y-intercept. Okay, now it says write the inverse and graph. So the first thing I'm going to do is f of x doesn't help me out a whole lot here. I'm going to change that to a y. Okay, then what I'm going to do is I'm going to flip-flop the x and the y around. And now I'm going to solve for the y. Okay, so to solve for y, I would have to add 5. So I get x plus 5 equals -1/2 y. Okay, well, in order to get rid of a -1/2, I want to multiply both sides by -2. Multiply by -2. So I'm going to get -2x minus 10 is going to equal y. Okay, or I can just flip-flop and turn it around so it looks a little bit more like something I'm used to seeing. Okay, with the y first. Okay, and if you want to go back in and change the y to an f of x, you certainly can. You don't have to, because remember, they mean the same thing. Alright, so this would be my inverse function. Okay, which technically I probably should go through and I should write it like this. Okay, so technically that whole f of x thing, you probably want to change it to inverse notation to make sure you don't get them confused. Okay, now as far as this is concerned, it's one of those things where I have to go ahead and graph or plot again to figure out what my inverse is going to look like. So if I go down, -10 would probably be all the way down here. And then I'd have to go, it'd be down 2 to the right one, or I could go up 2 to the left one. Okay, so I'm going to try to draw this in as best I can. Okay, that would be the graph of my inverse. And again, if you were to put the line y equals x through the middle of all this, alright, y equals x, okay, you would see how basically the points on each of those graphs are just flip-flops of each other. We flip-flop the x and the y to go ahead and get to whatever it is that we're trying to get to as far as an inverse is concerned. Alright, so again, let's look at what we got going on here. I'm going to graph my original. So I'm going to go up 2. It looks like this graph is by 2. So I'm going to go up 2. Alright, 2, 4, 6, yep, by 2s. Okay, and then my slope says 2 over 3. So I'm going to go up 2 over 3. Up 2 over 3. Or I could go down 2 and this way 3. Down 2 and this way 3. Alright. Okay, so that would be the graph of my original. Now, I'm going to change f of x to y and write out what I have, and then I'm going to flip-flop the x and the y. So x is going to equal 2/3 y plus 2. And now I'm going to go ahead and solve for the y. So the first thing I'd have to do is subtract the 2. So x minus 2 equals 2/3 y. Now, to get rid of 2/3, I'd have to multiply by 3 over 2. Now here's the key. Remember, when you multiply by 3 over 2 on this other side here, everything is getting multiplied by 3 over 2. So I have 3 over 2x minus, I have to take 3 over 2 times -2, which is actually going to be -6 over 2. Alright, I'll write it as -6 over 2 to start with. because remember this is technically over 1. Alright, and that's going to equal y. Now remember, negative 6 over 2 is basically like negative 3. So if I flip-flop this around and write it in inverse notation, then a 3 over 2x, alright, and then I'm going to go minus 3. Alright, so if I go down 3, and then I use my slope of up 3 over 2, up 3 over 2, up 3 over 2, up 3 over 2, and I'll draw it up there. Okay, and again, it's a little bit tough to see because we kind of run in a room in the top right corner there, but you can see again, if we divided this thing in half with the line y equals x, you'd see how x values and y values are basically flip-flopped on one side of that line or the other. Okay, so again, finding inverse functions, and a lot of people tend to have a little bit more success going about inverses this way, just because you can flip-flop x and y. You don't really have to think about what the opposites of different functions happen to be, what the opposites of different operations happen to be. Alright, and kind of go from there. Okay, so that's probably the easiest way if you were struggling a little bit with what we did before as far as trying to figure out inverse operations. This will certainly make things a little bit easier. Okay, so next thing we're going to do is we're just going to kind of apply this to a couple situations where knowing how to find an inverse would probably help us out a little bit here. Okay, so we're going to be given a situation like this. Juan buys a CD online for 20% off the list price. He has to pay $250 for shipping. The total charge is $13.70. What is the list price of the CD? Okay, so what we're going to look at is figuring out some type of cost function. So the cost, which we know is $13.70, but we'll wait to fill that in here in a second. So cost is $13.70, and it's one of those things here where you probably don't want to flip-flop variables around too much when we do this. So that's why we're going to try to figure out a function that represents the overall cost first, and then kind of go from there. Okay, so cost is $13.70, so the cost equals 20% off the original price. Okay, so basically we need to take 0.2 times the price, and then we have to pay $250 for the shipping. So plus $250. So again, if you take 20% of the price and add $250, that's supposed to equal $13.70. Okay, so what we're going to do now is, because we know what the cost is, I'm going to go ahead and put $13.70 in here. And in order to figure out the list price for the CD, or what P is, all right, I'm going to go ahead and I'm essentially just going to solve for P. So I'm going to subtract $250 over there. And if I take that away, I'm going to be left with 1125 equals 0.2P. All right, to figure out what the price is, we divide by 0.2, divide by 0.2. Okay, so 1125 divided by 0.2. %, off. Oh, here's my problem. Okay, now if I did that, I get a weirdly large number, and that's because, okay, what I did up here is, and it's a common mistake that you see with these problems sometimes, okay, is I put in 0.2 of the price. Well, he didn't pay for 0.2 of the price. He did get 20% off. This actually should have been a 0.8 in here, because if you get 20% off, you pay for 80% of it. All right, so I should have had 0.8s in here instead. All right, and again, it's just a common mistake. We see 20%, and automatically we think, well, 20% off the price. Well, you do get 20% off, but the problem is you actually pay 0.8. Okay, so 80%, we should have been dividing down here by 0.8, not 0.2. Okay, so 1125 divided by 0.8, you're going to get a more realistic number where the price is going to be right around $14 something like that. Okay, so that would be the original price of what's going on there. Now again, like I said, anytime you're getting a percentage off, you have to remember when you're trying to figure out a cost function, you need to make sure you understand that you're not paying for 20% of something. You're actually paying for the other 80% of it in this case. Okay, and if you put the wrong number in here, like I had a 0.2, when I did this step down here, if I divide 11.25 by 0.2 instead of 0.8, you get like 56, and that completely throws off your problem a little bit there. Okay, so you just need to make sure when you're figuring out your functions and all that stuff, your cost functions, that you think about what are you actually paying for. Okay, so just a little thing to be aware of when you go through problems like this. Now again, just remember, even though you know what the total is, okay, I want you to just think about, okay, well, I still want to write a cost function like this before I actually fill in my value there. Okay, so make sure you understand what variable is representing before you start solving and trying to do all things that way. All right, now that basically brings us to the end of what I'm looking at here as far as inverses and how to apply them and all that stuff goes. All right, so I know this was kind of quick and kind of getting through this. Make sure you understand the process of using inverse operations as far as, you know, if I added something, that means the inverse would have to involve subtracting something. But what becomes a lot easier would be the second way we went through it, where you basically fill y in for f of x and flip-flop your x and y around, and then go ahead and solve for y again, and that'll get you your inverse. And usually it's a lot easier to make sure that your inverse is correct when you go ahead and do that. Now, if you do ever want to go check to make sure that all this stuff is working, when you get your original and you compare it to your inverse, remember, if you fill into one of them, okay, if we fill into the original and say you fill 1 into your original and you get 3 out, okay, when you fill 3 into your inverse, you should get 1 out, kind of like that slide way back here at the beginning. I'll go back to it real quick here. Right here. Okay, remember, basically your inverse undoes what your function just did. So if you take the output of your original function and put it into your inverse, all right, you should get back to whatever your original input was that you filled into your function. So remember, an inverse basically undoes whatever your original function did. So that's one way to check and make sure that your inverse really is an inverse of the function. It should undo anything that the normal function does. So pick an easy number like 1, fill it in. You know, if I fill 1 in here, 1 plus 6 would be 7. All right, now if I go back down to the bottom, if I take that 7 minus 6 would give me 1. So essentially the inverse should undo whatever it is your original did. Okay, one of those deals where, again, you should have plenty of information to get started on your homework. If you have any questions, just make sure you ask, but come to class prepared and ready to ask questions on some of the stuff that you might not be sure about.